Imagine a future where humanity transcends its most fundamental biological limitation, the absolute need for oxygen. What if we could survive, even thrive, in environments completely devoid of breathable air? Our current existence is intricately tied to oxygen, a vital element that powers every cell in our bodies, especially our highly demanding brains. Without a constant supply, our biological systems rapidly fail, leading to irreversible damage and, ultimately, death within minutes. This is our current reality. Today, we'll explore the harsh science of anoxia, delve into hypothetical solutions, and consider the profound implications for space, medicine, and the very definition of human potential. At the core of our oxygen dependency is cellular respiration, the metabolic pathway that converts nutrients into adenosine triphosphate, or ADP, the energy currency of life. Oxygen acts as the final electron acceptor in this process, a crucial step that allows our cells to efficiently generate the vast amounts of energy they need to function. When oxygen levels in the body drop, a condition known as hypoxia sets in. If oxygen is completely absent, it becomes anoxia, a far more critical and life-threatening state. The brain, consuming approximately 20% of the body's total oxygen and glucose, is exceptionally vulnerable to anoxia. It has very limited energy reserves. Without oxygen, neurons cannot produce enough ADP, leading to a rapid cascade of cellular dysfunction and death. This process is swift and devastating. Within just 30 seconds of anoxia, consciousness is lost. Irreversible brain damage can begin in as little as 4 to 6 minutes, making immediate intervention crucial. This rapid deterioration is why conditions like cardiac arrest or severe respiratory failure are so dangerous, as every second without oxygen counts. But what if we could circumvent this biological bottleneck? Scientists are actively exploring radical concepts to extend human survival in oxygen deprived conditions. One promising avenue involves artificial blood substitutes. These engineered compounds aim to mimic or even surpass the oxygen carrying capacity of natural blood. Perfluorocarbons, for example, are liquid chemicals capable of dissolving large amounts of gases, including oxygen. They've been studied for their potential as temporary blood replacements in emergencies. Unlike hemoglobin, which binds oxygen, perfluorocarbons simply dissolve it, allowing for direct delivery to tissues without complex biological interactions. Another revolutionary approach focuses on advanced external life support systems, far beyond current rebreathers or spacesuits. Imagine microoxygenators, tiny devices either implanted or worn externally, designed to deliver oxygen directly to critical organs like the brain and heart, bypassing the lungs entirely. These systems could potentially utilize electrochemical processes to extract oxygen from ambient non-breathable gases or even generate it from stored compounds. Metabolic suppression is another fascinating concept. By safely slowing down the body's energy demands, oxygen consumption could be drastically reduced. This is akin to how some animals enter states of hibernation or torpor, surviving for extended periods with minimal oxygen and energy expenditure. The implications of achieving oxygen-independent survival are truly profound, opening up entirely new frontiers for human exploration and medical intervention. For space exploration, this capability would be nothing short of revolutionary. Astronauts could venture into environments currently deemed utterly uninhabitable. Planets like Mars, with its thin, unbreathable atmosphere, or even the deep space void, would become accessible without the constant, bulky reliance on complex life support systems. Deep sea exploration would also be transformed. The crushing pressures and lack of oxygen in the abyssal zones currently limit human presence to specialized submersibles. Imagine divers exploring hydrothermal vents or uncharted trenches directly, equipped with personal systems that negate the need for external oxygen tanks and allow for extended stays. In medicine, the applications are equally transformative. Emergency situations involving cardiac arrest or stroke, where oxygen deprivation is critical, could see vastly improved outcomes. Patients awaiting organ transplants could be kept in a state of suspended animation, extending the viability of organs and dramatically increasing survival rates. This technology could also revolutionize surgery, allowing for longer, more complex procedures without the risk of hypoxic injury to tissues, pushing the boundaries of what's surgically possible. The ability to survive without oxygen remains a distant, yet incredibly captivating, scientific frontier. It challenges our fundamental understanding of human biology and resilience. From the rapid death of brain cells to the potential of artificial blood and advanced life support, the journey is one of immense scientific and technological hurdles. Yet, the implications for space exploration, deep sea discovery, and medical advancements are too significant to ignore, promising a future of unprecedented human capability. As we continue to push the boundaries of what's possible, we inch closer to a future where human evolution is not solely dictated by natural selection, but also by our boundless ingenuity and scientific ambition. The question of surviving without oxygen is not just about overcoming a biological limitation. It's about envisioning a future where humanity's reach knows no bounds, extending our presence across the cosmos and into the deepest parts of our own planet.